get started? Fermi, are you
yeah
set up? Okay, great. So let's get started. Welcome everybody, and yeah, welcome to this this edition of this Simon's Quantum Colloquium. So it's a real pleasure to have Fermi Ma speak today. So Fermi is a Simon's Berkeley postdoc and a Simon's Quantum postdoc. He just finished his PhD with Mark Zandri at Princeton, and on quantum security and Fiat-Shamir and cryptographic protocols. He's been doing this beautiful work at the intersection of quantum and crypto, and really looking forward to this talk. So, Fermi.
Right, thanks so much, Umesh, for the really kind intro. Right, so I'll be talking about post-quantum succinct arguments, breaking the quantum rewinding barrier. This is the work I did at Princeton. This is a joint work with Alessandro Chiesa, Nick Spooner, and Mark Zandri. So before I continue, everyone can see the slide okay? This is the right view. Okay. So I want to start off with a very broad question. So why are quantum computers a threat to cryptography? And I really want to explore this answer. So to give a good answer to this, let's recall how cryptographers actually prove security. So say you've written down some cryptographic protocol or construction, and you want to show that it satisfies some sort of security definition. Well, the way that you formally prove this is your crypto security proof usually comes with two components. And the first part, which is usually necessary, is this computational hardness assumption. And this is something like hardness of inverting only function, hardness of factoring. And you couple this with a security reduction. And the security reduction needs to say that any efficient attack on your protocol or on your construction gives you directly a way to break the underlying hardness assumption. So as long as you have confidence that your hard problem is, well, hard, then you should be able to conclude that your cryptographic protocol is actually secure. Okay, so it's a really simple formula, but with this in mind, why are quantum computers a threat? And the simple answer to this that most people are familiar with is, well, Shor's algorithm is just going to break a lot of the widely used hardness assumptions. Right, so we're going to lose things like factoring and discrete log, which are not hard against quantum computers. And unfortunately, these are actually the things that underlie a lot of the public key crypto we use in the internet today. So when it comes to building cryptography secure against quantum attacks, aka post-quantum cryptography, the minimum requirement is that your underlying hard problem had better be hard against quantum computers. It's sort of an obvious requirement. The good news is that we have candidate hard problems. So for instance, various problems on lattices and isogenies. But a common misconception is that for quantum attacks, the only thing you need to do is worry about the underlying assumption, that you can take sort of any cryptographic protocol that you've already proven secure and just swap out a quantumly broken assumption for a quantumly hard assumption. And the reason this isn't the only thing you need to do is that you're missing the other half of the equation. And the key point I'm making here is that the security reduction itself has to be quantum compatible. So if you've already proven classical security of your protocol, then you probably wrote down a classical reduction. And formally, what your classical reduction shows is that any classical attack on the protocol turns into an attack on the assumption. But what you want to do is couple your reduction with your assumption, right? And so if you want quantum security, what your reduction has to say is that any quantum attack on the protocol leads to a quantum attack on the assumption, right? So the question then is, what classical reductions are actually going to be quantum compatible? Well, it turns out a good fraction of classical reductions are sort of trivially quantum compatible. It's sort of a matter of taking your security proof and replacing probabilistic polynomial time with quantum polynomial time. But in other cases, this isn't the case. In other cases, the reduction may do things that makes the reduction not quantum compatible. Sort of the prime example of this is rewinding the adversary. So for instance, you might have an interactive protocol where it's proved secure by arguing that midway through the interaction, the reduction can save the adversary state and then run it many times in multiple challenges. So you might have something that looks like this picture, say a 3-message protocol, where you prove security against a malicious prover by having the prover send a first message and then querying it on some second message and recording its response. So you write down this transcript, and then you reset it back to the adversary state as it was after that first message, and then have a whole new interaction from that point. So you sample a new challenge, ask it a question, get the answer, record this, and maybe your reduction is going to use the ability to record these multiple transcripts to break some hard problem. So if this seems a little bit abstract, don't worry, I'm going to make this more concrete and give an example that you can actually feel later on. But this is basically the mechanic that I'm talking about when I'm saying that a reduction may rewind the adversary. Okay, so the problem that we're running into is that it's unclear how to do this when the adversary is quantum. Right, so it's sort of straightforward to say that if I have a classical adversary, I can just record its state, its classical information. But if it's a quantum adversary, then its state is it's now a quantum state. And the problem is that when I run it the first time, I record this answer Z, that might be a measurement of the quantum state. And we might have an adversary that detects this measurement. And once it realizes it's been measured, it's going to stop responding to you. It's going to stop giving you valid responses. And if your reduction is hinging on the fact that you can get many valid responses to break some hard problem, then it's not clear how you're going to get any more after that first one. So this is really the core of the issue. So for this talk, I'm going to phrase the goal of rewinding as basically to solve this problem, that I have an adversary that can answer me once, and my goal is to get my adversary to answer me on multiple challenges, and I want to record its responses. So before I go on, I want to have a sort of brief disclaimer that this is how rewinding is commonly used to prove soundness, but doesn't fully capture applications such as zero knowledge, where sometimes you might want to be able to, say, simulate the adversary state, or maybe the explicit goal is not to get multiple transcripts and record them, but to get sort of one favorable response from the adversary that your simulator can deal with. But if it's something you haven't heard about before, don't worry about it. It's not really what we're going to talk about today. So for today, again, the focus will be on this problem of asking the adversary many questions and writing down its responses. And in particular, I'm going to make this concrete and focus on one protocol. So it's Killian's Succinct argument protocol. And this is a central result in cryptography that really captures the difficulty of this rewinding problem. So before I go on and explain what I mean, let me just recap what is a succinct argument. So I'll be talking about succinct arguments for NP. And basically, in a nutshell, what a succinct argument lets you do is it gives you this extremely efficient way to verify your NP statement. Okay, so we already think of NP as these statements that you can efficiently verify. But when we say efficient there, we mean polynomial in basically the size of the witness. And succinct arguments basically let you do much, much better than this. It reduces the verifier efficiency all the way down to being polylogarithmic in the size of the instance in the witness, with an additional polynomial dependence on a security parameter lambda. And the argument part of succinct argument is basically saying that you can only hope to get this succinctness guarantee, this massive savings, by relaxing your soundness. So you no longer have security against arbitrary cheating strategies, but only security against efficient cheating strategies. So argument rather than proof. Okay, so a seminal result of Kilian from 1992 constructs a 4-message succinct argument system. So four messages back and forth from the verifier to the prover verifier messages. It constructs this for all of NP, assuming just collision-resistant hash functions, or CRHFs, which is a pretty mild cryptographic assumption. So let me sort of rephrase. This is a really remarkable statement, right? It's saying, under a mild computational assumption, any NP statement can be verified in time that's polylogarithmic in the size of the instance of witness. So I think it's a truly remarkable result. And of course, there's been many, many applications of this in both theory and in practice. But despite this importance of Killian's protocol, the post-quantum soundness of Killian's protocol has remained open for sort of all this time. And the reason for this is in the rewinding that's necessary to prove soundness. In particular, the way that we know how to prove the classical soundness of Killian's protocol is to rewind the attacker many, many times. Essentially, we need to get an arbitrary polynomial number of accepting transcripts from the adversary. And we do have some quantum rewinding techniques, but they're actually fundamentally stuck at a far smaller, actually constant number of rewinds. So that's really the gap, that we know how to rewind an attacker a constant number of times, but the soundness of Kilian needs us to get all the way up to an arbitrary polynomial. So in this work, we resolve this problem. The one-line contribution to this work is we give a general rewinding technique to rewind a quantum adversary as many times as desired. And the big consequence of this is that now we know that Killian's protocol is post-quantum sound, as long as the collision-resistant hash function is quantum binding. So this is a slight strengthening of the classical notion of collision resistance. It's turned out to be the standard definition of binding against quantum adversaries, and this is a definition of Unruh. And these exist under standard post-quantum assumptions, such as the quantum hardness of learning with errors. Another consequence of this is that many other protocols, so for instance, various things called sigma protocols. So examples are these 3-message protocols by GMW and Blum. And these protocols have optimal post-quantum soundness guarantees. So these protocols were previously proved to be post-quantum sound, but with massive losses in parameters. And with this rewinding technique, we can show that the quantum security is essentially as good as the classical security. Okay, so let me dive in and just let's recall Killian's protocol first before we go into the rewinding details. So Killian's protocol starts with a probabilistically checkable proof, and it turns this into an interactive argument system using cryptography. Okay, so what do I mean? A PCP is basically a highly redundant NP witness, and it's written in such a way that I can have this PCP string down, this PCP string pi, and a verifier can come by and just query a few random positions of this PCP, particularly a polylog number of positions, and be convinced with overwhelming probability to accept or reject. Okay, but this PCP doesn't give you a really efficient way to just, for one party to convince another party that an NP statement is true, because it relies on this modeling assumption that the string is written down first, and then the verifier comes by and randomly looks at a few positions. You can't change the answers based on what the verifier wants to look at. And so if you just sort of naively try to turn it into an interactive argument system, interactive proof system, you're not going to get soundness. It's going to be possible to cheat by answering based on what positions the verifier is looking at. So Killian's protocol uses cryptography to solve this problem. Basically, the idea is to have the prover commit first to the PCP, send a short commitment to this PCP before you do the PCP verification. So let me go into a little more detail. The first thing the prover is going to do is take its NP witness and code it as a PCP. It's going to get this collision resistant hash function H from the verifier. And the first thing it's going to do is it's going to hash this PCP up in this tree structure. So it's called a Merkle tree. Basically, this hash function H has a property that takes inputs of length 2n and spits out outputs of length n. So it cuts the length in half. And so you apply this to blocks of size 2n of your PCP, and this hashes it up, and now you have something that's half the length. And then you just keep going. You iterate this process until you get a single CRHF output, and that's going to be your root of your Merkle tree. And you send that as the commitment. Okay, so this commitment has a property that is short. So it's independent of the length of the PCP. And the interesting property of this commitment that we're going to use is that it has this local opening property. So in particular, when the verifier wants to run a PCP verification that samples PCP random coins R and asks the prover to open this PCP at positions corresponding to R, so denoted Q sub R, this Merkle tree allows the prover to open this position and convince the verifier that it's doing it honestly without having to go through the naive approach of revealing every single leaf of the tree. Right? That's one way you can open this commitment. But the Merkle tree gives you a shortcut. It allows you to open a much smaller, a log number of positions. So in particular, if the prover wants to reveal the value of this black square, then it can just look at the path from that leaf to the root and include all the siblings along this path. So these blue squares. And if the prover sends over these black squares and the blue squares, which will constitute the opening proof, then the verifier can just recompute its way up the tree and verify that this actually reconstructs the committed value the prover sent earlier. So this will convince the verifier that indeed the prover is answering honestly. And so in the end, the verifier should accept or reject, it should accept if and only if all the openings are valid and the PCP verifier accepts. Okay, so the intuition for soundness is you want to show that the CRHF, this collision resistant hash function, is forcing a malicious prover to respond consistently with some PCP string pi, right? And then you will appeal to the soundness of the PCP system that says that if X is not in the language, then there is no convincing PCP. So the way that you formalize this, though, is, well, you can't just say that there is some PCP and the prover, may be consistent or inconsistent with it, because where do you get that PCP from? So the way you formalize this is you rewind the last two messages many, many times. You keep querying the prover and random questions and get recording its answers. And you basically piece together these answers and you form a PCP yourself. And once you get enough of these answers, something interesting happens. So you record many of these accepting transcripts, these RIZIs. And these answers are going to overlap, right? The PCP is only so long, and you'll query it enough times that you're going to have some overlaps. And either all these overlaps are going to be consistent with each other, in which case all the answers RIZI you get are going to piece together to give some PCP. But what you can show is that this is going to be impossible, because what's going to happen is the PCP you construct is going to have the same convincing probability as your prover, or close to it. And if your prover's success probability is too high, then such a PCP won't exist. So the only other option is that the transcripts you're recording are not consistent with each other. That means there's going to be some transcript, like some pair of transcripts that disagree on some position. And the structure of this Merkle tree will guarantee that anytime that happens, you can find a collision in the hash function. So this is really how the classical reduction goes, that because the PCP system is sound, if you have a prover who's fooling your verifier, eventually you're bound to find a collision in the hash function. Okay, so now I want to zoom in on sort of where all the action is happening, which is in these last two messages of the protocol. So we're basically playing a game where I ask it a question, I ask this prover R, I get an answer Z, and I record it, and based on some public predicate V, I either accept or reject. Okay, so this is the game. I'm going to remove the first two messages of the protocol because I can sort of hard code them into this predicate. And I should note that this V is really publicly checkable. Both the prover and verifier can determine if R or Z will convince the verifier. Okay, so this is the game we're looking at. And at this point, the adversary has some state S. And so in the quantum setting, this adversary may have some quantum state at this point. And this is the state that the adversarial prover has accumulated by this point in the protocol. Maybe it did some measurements, it did some arbitrary quantum operations to send those first two messages. So now it has some quantum state. And I want to talk about the success probability of this quantum state S. In particular, this is going to be the probability that this prover with state S convinces the verifier in this interaction. This probability in particular is over the randomness of R. Okay, so this may be the one thing to memorize, that when I say success probability of a state, what I mean is the probability that the adversary with this state wins in the game where I ask it a random question R. Okay, so here's our goal. We're given some adversary state S, the success probability, say 1 over poly, and we want to output many accepting transcripts RIZI. And I claim that what we've seen so far shows that the soundness of Kilian really reduces to this question, like, can I do this? Okay, so for the rest of the talk, I'm just going to focus on solving this particular goal. All right, so just to make sure everything's making sense, Sandy, check this. When S is classical, this is a really easy thing to do. Right? You can just run many trials, because after each trial, you can reset the prover state back to what it was. And so if you're winning on a 1 over poly, if you're winning with 1 over poly probability in each trial, then you can get any number of transcripts you want by running enough trials. Okay, but when S is quantum, you can't reset the state, since a single trial requires measuring this answer Z, and that may disturb the state. And more concretely, the reason why we're concerned about the state disturbance is that the success probability of the adversary may go down. So initially, you have an adversary with success probability P, and after querying it and disturbing the state, its success probability may drop to something much smaller than P. Okay, so what do we do in this work? I'm just going to give a high-level overview of what we do, and then spend the rest of the talk filling out this template. So what we do is we implement this repair procedure. And the goal of this repair procedure is to reset the adversary's success probability. So I'm going to take in this damage state, this S prime, and the result of my repair procedure is a new adversary state S1, whose success probability has somehow been reset back to the original success probability of P. And I want to emphasize that this adversary is not necessarily the same as the original one we had. This S1 state could be different than my initial state S. But that doesn't really matter. The only thing that matters is my ability to record many transcripts. So it's fine that I have a different state now, so long as my new state still has that success probability of P. And so now I can ask it a question again, get an answer. I record an accepting transcript with good probability. I've damaged the state again, and then I can just keep repeating this process. So every time I damage a state, I have to run this repair algorithm. And using this, as long as my repair algorithms repair success probability enough, I can rewind any number of times I want to. And so the focus of this talk is going to be, how do we construct a procedure, repair, that sort of does this magic? How do you take a disturbed adversary state and restore the success probability? Okay, so before I get into the details of how repair works, I wanted to recall a technique of Unruh that's going to make our lives a little bit easier. It's going to sort of reduce the magnitude of the problem we're dealing with. So what I mean is, using a technique of Unruh, you can reduce the problem of measuring the prover's response to measuring the verifier's decision. And intuitively, this reduces the amount of disturbance that you're causing to the prover's state. So let me explain. The way that we run this trial is you ask a question R, and then you record an answer Z. And the naive way of doing this is, well, the adversary in full generality is repairing some superposition of answers. And if you want a classical answer, well, you just measure the superposition right away. So this is the straightforward way to do it. But there's also this lazy way of doing it, right? We use the fact that you only care about recording Z when RZ is actually going to convince the verifier. So what you're going to do is take advantage of that observation to limit the disturbance. And so you'll leave Z in superposition. Instead, just compute first whether or not the verifier will accept. So compute the decision of the verifier. And then only if the verifier accepts are you going to go back and measure the contents of the Z register. Okay, so this is equivalent to the measurement on the left, except that it potentially disturbs the adversary less. And the nice observation of Unruh is that there are certain protocols where you can really take advantage of this lazy measurement structure. In particular, if your protocol has unique responses, meaning that for any challenge R, there's only a single string Z that would ever convince the verifier, then the step 2 measurement is actually not going to disturb the adversary state at all, right? Because once you've measured that V of RZ equals 1, and you know R, then Z is uniquely determined. So the register containing Z can only contain a single string. And so measuring it is not going to disturb anything. So this lazy measurement really reduces the amount of disturbance, right? Previously, you were measuring a whole string. And now if you only disturb the adversary's state in step 1, you're only causing a 1-bit measurement of disturbance to the adversary state, just the output of the verifier's decision. All right, well, Killians Protocol doesn't actually have this property. It doesn't have unique responses. However, it turns out it has something that's just good enough. It turns out that if the hash function H has this quantum binding property I've mentioned, it's also known as collapsing, then step 2 is computationally undetectable to the adversary, meaning that the adversary can't tell the difference between 2 different worlds, one world in which I don't do the second measurement and a world in which I do it. So therefore, it suffices for the rest of this talk to only perform step 1. So we're just going to try to make the verifier accept on many random challenges. And the reason this is going to suffice is that this will imply a full reduction that performs both steps 1 and 2, meaning that every time it queries, it actually records a transcript. And the reason this suffices is because step 2 is computationally undetectable. So if your reduction is going to work in the first setting, it'll still work in the second setting, as long as your reduction is efficient. So the takeaway from all this, the reason why I'm recalling Unruh's observation here, is that we've reduced this problem. We can just measure the verifier's decision. And so you only have to repair the state after it's been disturbed by this 1-bit measurement. Okay, so with this in mind, let's turn to the new stuff. What do we do? How do we implement this state repair? Okay, so we have this new picture, right? The difference in this picture is now the output of the prover is only a single bit, this verifier's decision. And the high-level idea is we're going to try to identify this good subspace pi p. And by the way, when I write pi p, I mean really I mean both a linear subspace of quantum states as well as the projection operator, the projection onto this subspace. So I'm going to identify a good subspace pi p, where the original adversary state S is in pi p. And moreover, the crucial property is that all states in pi p have success probability at least p. This is the defining characteristic of this pi p subspace. Okay, I haven't said where this comes from. It should not be clear where it comes from at the moment. But let's say magically that we have a subspace pi p that satisfies these properties. Okay, then the way that we're going to do state repair is we're going to alternate two projective measurements back and forth until the state is back in pi p. Right, and once the state is in pi p, then we know we have a good state again, because the defining property of pi p is if you're in the subspace, you have success probability p. Okay, so what are the two measurements we alternate back and forth? The first is the binary measurement of pi r, which corresponds to the measurement that disturbed S. Right, so we initially had this state S. I said we did a binary measurement to disturb it and produce this post-measurement state S prime. And pi r is going to be the measurement that we just applied. So I'm defining it so that S prime is in pi r. But yeah, so this is the measurement we just applied. And the measurement we alternate with this is going to be the measurement onto pi p. Okay, so by the way, when I write a binary measurement, I'm going to write it as a tuple of one projector and then the orthogonal projector. Okay, so what we're going to do is start from S prime, this is start state, and we're going to first apply this measurement onto pi p. And the goal is to try to get this measurement to accept, right? Because if this measurement accepts, because it's a projective measurement, the post-measurement state is now going to be in pi p. And so our hope is we can apply this and get it to accept. But if it rejects, then what we're going to keep doing is apply the other measurement. So we apply pi r. Regardless of the outcome, we have to keep going. Apply pi p. And this time, say it accepts, then we're done. Right now, the post-measurement state is in pi p. So there's only 3 measurements because the slide is only so big, but we could just run this for as long as we need to until pi p accepts. So this is the high-level approach that we're going to try to instantiate. Okay, so there's a huge missing chunks here. So first off, how do you know this process actually terminates? Like if I'm going to keep alternating 2 measurements back and forth until one of them accepts, then I want some kind of guarantee that this is not going to run forever. And then the second big missing chunk is where in the world does this pi p measurement come from? Right? How do you measure that an adversary has success probability at least p? So it turns out that the first question is a little easier to deal with. So I'm going to resolve that detail first. So how do we know this process terminates? And the key is to use the fact that these are 2 binary outcome projective measurements. And imagine the 2-dimensional case where the picture is really simple. So if you're in 2 dimensions and you have projection, as long as it's a non-trivial projection, then the accepting subspace and the rejecting subspace are just 1-dimensional spaces and they form this right angle. And so if I have another projection pi r, then this other right angle is going to form is going to intersect at some, they're going to form an angle of theta with each other, right? So pi r and pi p have an angle of theta. And my 2 states are going to be S prime and S, right? So S is my original state, it's here in pi p, and my disturbed state is this S prime. And I want to label 2 more states. So S perp is a state perpendicular to S, and S prime perp is a state perpendicular to S prime. And in the 2-dimensional case, these are really the only 4 states that we're interested in. Because when you alternate the 2 measurements back and forth, your state will always jump between being in one of these 4 states. Right, so if I've applied the pi r measurement and it rejects, then I know that I'm at the S prime perp state. Right, if I applied the pi p measurement and it's accepted, I'm at the S state. So alternating the 2 measurements back and forth, I just keep jumping between these states, and the behavior really is determined by this angle theta. And what you can show based on sort of elementary properties of these projective measurements, that if you start at the state S in pi p, then you're going to return to pi p in expected O of 1 steps for any theta. So it's a fun fact that this works, that this returning to S is independent of theta. And you might think that maybe, well, that seems sort of implausible, right? What if pi r is really far away from pi p? It seems like it might take a long time to get back. But the point is that if pi r makes like an almost 90-degree angle with pi p, then you actually had a really small probability of landing there in the first place. And so that's accounted for in this expectation. Okay, so Jordan's lemma extends this analysis to higher dimensions. Basically, this lemma says that I can consider for any two projectors, I can decompose the space into a whole bunch of these two-dimensional slices. And so this two-dimensional slice analysis just readily extends as long as you have the right sort of claim. And so the only property I'm using here is the fact that these are two binary outcome projective measurements. I'm not using anything else about pi p and pi r. So that's a thing to keep in mind. Okay, and with that, as long as we know these measurements are projective, then we know that this process is going to terminate. Okay, so maybe the more tricky problem, how do we define this pi p? Right, I'm claiming that we have some measurement that measures whether or not an adversary has success probability at least p. And it turns out that as I've currently specified it, such a measurement is unlikely to be efficient. Something that exactly achieves this guarantee, we won't be able to achieve. But with if we relax the guarantee a little bit, then we can use this beautiful technique of Marriott and Watrous to solve our problem, or to at least implement this pi p. So let me recap what Marriott and Watrous do. They're concerned with this problem of witness preserving QMA amplification. In particular, given a QMA witness state, you want to compute with really high precision the probability the verifier will accept. And using this, you can boost the completeness soundness gap of QMA. But more generally, what they show is that given any binary output quantum circuit C, so what I mean by that is a circuit that writes its output onto a single register that you can measure. And along with the circuit, you're given an input state S, then there's a procedure to estimate the probability that C outputs 1 on S to arbitrary precision. And so what I mean by estimate, I'll formalize on the next slide, but we're basically trying to compute this probability. And the key is that you can do this with only one copy of the state. And so that's why it's going to be useful for us, where we only have one copy of the adversary state. Okay, so this can be done for any quantum circuit. And so I'm going to plug in the quantum circuit that makes this procedure compute success probabilities for us. So remember, success probabilities are the probability you win this game where there's a random R and I measure your response. So I'm just going to turn this into a quantum circuit. And the natural way to do this is replace the classical randomness with the superposition of all challenges. And the circuit runs the adversary on the superposition of all challenges and just measures the verifier's decision. So if I run Marriott Watrous on this particular circuit, then I'm going to get this estimator that estimates my success probability now. Because success probability is the probability the circuit outputs 1. Okay, so for this talk, I'm going to need two key properties about this Marriott Watrous estimator. So the first key property is that these estimates, the outputs of this estimator, this P, they really have something to do with the success probability P naught. Right, so I have initial state S with success probability P naught. And my claim is that the output of this estimator, the expected value of this output is equal to my original success probability. Right, so it says your estimator is centered around the right mean. And the second key property we're going to use is this maybe curious looking property that says, well, if I run Marriott Watrous once and I get the state SP, then if I run it again, my next estimate is going to be fairly close to my previous one. Okay, so I'm starting with any state S. I run Marriott Watrous twice. I get two outcomes P and Q. And the claim is that P and Q are going to be close with high probability. So formally, this is some sort of epsilon delta guarantee. Formally, you can show that the probability P and Q are at most are within epsilon of each other, is at least 1 minus delta. And to achieve these guarantees, you need to run your internal Marriott Watrous estimator for some polynomial in 1 over epsilon and log of 1 over delta. So in particular, you can make epsilon arbitrary inverse polynomial, and you can make delta some exponentially small value. Okay, so before I go on, I want to kind of clarify that, like, while this sounds like a really well-behaved estimator, its behavior kind of defies your classical intuition. Really, these outputs P can be really like spread out. The only thing we're saying is that their expectation is P0. And moreover, once you observe a particular output, then your future estimates are going to be really close to what you just observed. If that sounds familiar, that's actually the sort of the defining feature of a projective measurement, right? That the measurement outcomes could be all over the place. But once I do the measurement once, a projective measurement has a property that if I do it again, I'm always going to get the same outcome. And so in that sense, Marriott-Watrous is this almost projective measurement. The output is like behaved in an almost projective way, because if I do a projective measurement twice, I'll always get the same outcome. Here, if I do it twice, I get two outcomes that are really close. So I'm going to call this an epsilon delta almost projective measurement. All right, so now I have this estimator, and my goal is going to be to plug it into my state repair template and see if I can use it to actually fix success probability. Okay, so recall where we were at. We had this high-level approach in mind, where we were assuming this whole time that we could measure this projector pi p, this projection on the states with success probability at least p. So in reality, we don't have this, but the closest thing we have is basically the analog of this procedure using Marriott-Watrous. Right? So instead of exactly knowing success probability, what we're going to do is run this measurement MWP, which I'm defining to mean the measurement that runs Marriott-Watrous estimation, and it accepts if the output is at least p. And so this is sort of the closest thing you can get. And we can easily swap out these pi p measurements for MWP. This is a binary measurement, right? I'm only recording whether or not the output is bigger than p or not. I'm sort of throwing away the rest. So these are really binary outcome measurements, MWP. And so I'm going to swap out the pi p's for MWP in my picture above. But I also need to update the invariant that I'm maintaining. And so previously, I was saying that the invariant we want to maintain is that your initial state before repair and your state after repair are both in the subspace pi p. And I was using that as a proxy to say that the state has good success probability, because being in pi p means your success probability is p. But we don't have pi p in reality, so I want to phrase my invariant in terms of a procedure I actually have. So fortunately, there is a natural Marriott-Watrous analog of being in pi p. So the way to think about this is the invariant I was maintaining before is a property that if I were to measure your state with the pi p projective measurement, it would return 1 with certainty. The analog I have here, because the outcomes of Marriott-Watrous I can't know with certainty, is that if I apply the Marriott-Watrous estimation procedure to your state, then it'll spit out an outcome that's at least p with 1 minus delta probability. And it turns out I can set this delta to be the same delta in the epsilon delta almost projectiveness. So this delta is going to be negligibly small. Okay. So what does this mean if I have this guarantee that the probability that MWP on S outputs 1 with overwhelming probability? Well, in particular, that allows me to lower bound the expected output of running a Marriott-Watrous estimator on your state. Right? Because I know that it's going to, if I run estimation on my state, I get an output that's at least p with high probability. And so that means that my expected output is at least p minus this delta. And remember one of the defining properties of this estimator that we're using is that this expectation is actually equal to the success probability of S. So therefore, this p minus delta lower bound on the expected output of the Marriott-Watrous estimator also allows me to say that my state S has this much success probability. Okay, great. So now I'm gonna swap out my old invariant for this new one. And I want to note before I continue that this guarantee necessarily degrades with time. So previously I was trying to restore this invariant exactly, but the actual property that we're going to write down is going to get worse. So the very first time that my starting state S might satisfy the guarantee that the estimator outputs at least p with probability 1 minus delta. But my repair state is only going to have the property that we estimate at least p minus epsilon with probability at 1 minus delta. And the reason for this is sort of just zoom in on the last thing that happens, which was that we measured the Marriott-Watrous, we measured MWP, and it accepted. What does that mean? It means that I observed an outcome that was at least p. And my epsilon delta almost projective guarantee says that my next outcome with at least 1 minus delta probability will be no more than epsilon far away. But epsilon far away from p is p minus epsilon. So I can only guarantee that my new success probability or my new guarantee is phrased in terms of p minus epsilon. So I have this loss here, but it's not going to be a big deal. I can set the epsilon to be as small as I want. So if I know how many times I need to do repair, I can make sure this epsilon is small enough that we don't have to deal with it. But this is sort of the big qualitative difference between what we can actually instantiate and the ideal version of what we want. Okay, so this approach seems quite promising. It's getting us pretty close, but we do have a serious problem. And the problem is that the proof that we gave that this procedure would eventually terminate requires that these measurements are actually projective. But this MWP measurement, this binary measurement I wrote down, it's not projective. In particular, there is always some chance that if I run it twice, you can get two different outcomes. So this is sort of the technical crux of what we need to resolve to make this work. It's that we have a really simple template that when you put it all together, it's going to do rewinding. And the major component of this template, we already know how to do. But actually piecing it together, they don't quite fit. Because what the template needs from this piece is not satisfied by what the estimator gives us. Okay, so maybe the most natural idea is, well, you use the fact that any quantum measurement in general can always be made projective as long as you enlarge the space that it's acting on. Right, so this is a simple quantum fact that I can define a projector on a larger Hilbert space now. So I'm going to start labeling my spaces. And originally, my adversary state was on this A register. And I can measure it with this MWP. And I'm defining this projective measurement pi p star on a larger space so that applying pi p star to S prime tensor 0 on the W register is equivalent to applying the Marriott-Watrous measurement on S prime. And so this ability to take a quantum measurement and make it projective over a larger space, in particular, the way you instantiate this is by tensoring on some additional 0 registers and then applying a projective measurement to this whole state. So from this point on, A is going to denote the adversary register, and W is going to be this workspace ancilla register that you need to implement this pi p star. Okay, so it seems simple, but we have to be really careful here, because the outcome of measuring pi p star only corresponds to this Marriott-Watrous estimate when the W register is 0. This was the definition of pi p star, but in particular, we're not guaranteed anything about the behavior of pi p star if I set this W register to be something other than 0. So for instance, like regardless of the quality of my adversary state, maybe my adversary is totally junk, never accepts or never convinces the prover, the verifier. Maybe I could have this useless adversary state and tensor on like ones in the W register. And perhaps my projector always accepts when this is the case. So I have to be really careful that I only apply this pi p star in a way that's meaningful, because pi p star only corresponds to Marriott-Watrous when the W register is 0. Okay, and even if you start with the W register initialized to 0 before you alternate your measurements back and forth, the problem is that you're measuring this pi p star many times potentially. And even the first time you measure it, it may ruin the W register. It may make it non-zero, right? And once the W register is non-zero, then just seeing this measurement accepts does not necessarily tell you that the adversary is doing anything meaningful. Okay. So this is the problem with this sort of straightforward fix of just make it projective and plug it in. Okay, so the key idea to resolving this issue is you have to make use of the other projector, this pi r, which we sort of left alone this whole time. And it turns out the right thing to do, and it's maybe not so obvious that this is the right thing to do a priori, but you can prove it. The right thing to do is to extend this pi r projector to also project the W register onto 0. Okay, so intuitively, the way to think of this is that pi r was the disturbance of the adversary register, and it has this W register that kind of is it doesn't care about, and I'm going to redefine it to force that W register to be 0. And so this way, the intuition is that when I alternate pi r star and pi p star back and forth, the pi r star projection is going to keep trying to reset your ancilla registers to 0, so that the following measurement of pi p star is going to be meaningful. Okay, so this is just intuition, it's not formal. And the problem is that this is just a measurement, right? So it can't actually force an outcome. It can't force the W registers to actually be 0 because the measurement could reject and the W register could be orthogonal to 0. So it doesn't quite capture the intuition, but that's sort of the thing to keep in mind. And with this is essentially the full repaired procedure, that all you do is you start with your disturbed state, you tensor in a 0 in the W register, and then with these two measurements, pi p star and pi r star, you alternate them back and forth, and eventually pi p star will accept by the same argument we gave earlier. Then you get some adversary, or then you get some state psi that is defined in these A and W registers. And what you're going to do is you'll have to discard the W register because that part doesn't correspond to the adversary. And then you get some state S1. And the hope is that S1 has some guarantee about its success probability, or in particular that the Marriott-Waters procedure is likely to spit out at least p minus epsilon. Okay, so what remains now that we've stated the whole procedure is to show that this actually works, right? That at the end, we actually have a state S1 satisfying this invariant again. Okay, so this part is quite delicate, and it's going to require a lot more work. So I'm just going to give a really brief sketch of the key ideas behind it. And so fundamentally, the reason why this works is apparent when you look at the two-dimensional case. So let's consider 2D. So pi r star and pi p star are now right angles again in a 2D plane. And my initial state is this red vector, this S prime, the disturbed state tensored with 0 on the W register. And remember that in the 2D case, when I alternate pi r star and pi p star back and forth, I'm just going to keep hopping around until I'm at this particular green vector, which I'm labeling psi. And it turns out that the guarantee you end up getting on the resulting adversary state, which is the state you get from taking a psi and tracing out the W register. Turns out the guarantee you get in S1, that state, is going to depend on the angle between this red vector and this green vector, theta. And so I'm saying gamma is equal to cosine squared of theta. In particular, gamma is equal to the probability that the pi p star measurement accepts on S prime 0, which can be interpreted as the probability that MWP accepts on S prime. And so the conclusion you can get, and this is not obvious from what's on the slide, but you can prove it, is that your eventual state S1 will have the guarantee that the probability that the Marriott-Waters procedure outputs at least p minus epsilon on S1 is not quite 1 minus delta, but it's this degraded guarantee of 1 minus delta over gamma, right? Where gamma is this cosine squared of this theta angle. So what I'm saying here is that in the two-dimensional picture, the quality of the guarantee depends on the overlap between the red and green vectors. And in particular, remember that I can set delta to be really, really small. And as long as I set delta to be, as long as this delta was exponentially small, I was saying earlier, that then I could conclude S1 has success probability at least p minus epsilon. So here I have to worry about the possibility that gamma is also really small, right? So for instance, if gamma is just delta, then this guarantee is useless, right? Because then it's going to say it's 1 minus 1. So I need to make sure that gamma is not too small. And so that's the tricky part about doing the general case, is that to extend this two-dimensional analysis to the more general case of higher dimensions, we're going to use Jordan's lemma again and break down the analysis into a whole bunch of these two-dimensional slices. And we show that in the two-dimensional slices where gamma is really, really small, your state cannot possibly have too much weight there. And the intuition for this, I'm not going to show it very formally, but the intuition here is, like, think about this quantity, like expectation of MWP on a particular state. Initially, I had a state S such that this expectation was large. Like my initial state S had the invariant, right? That expectation of MWP in S was close to 1. And then I took my state S, I disturbed it by a binary outcome measurement. And the claim is that the resulting S prime the expectation of this quantity on S prime can't be that far away from 1 minus delta. Like it can be small, it can be inverse polynomial, but that's only going to happen with inverse polynomial probability. And it's not going to be exponentially small except with exponentially small probability. And so the key here really is that we only disturbed S by a 1-bit disturbance. And so properties that S satisfied are not going to be, that untrue for S prime. And because of that, this angle is not going to be that close to 90 degrees. And that's going to enforce that in all these two-dimensional subspaces, my guarantee is 1 minus delta over gamma, where gamma is not that tiny. And so collecting this together, you can get some overall guarantee that allows you to conclude that your state S1 has success probability fairly close to P minus epsilon. Okay, so let me start piecing this together.
Before you do, there's a question in the chat. It says, on fixing the W register, why not just uncompute it?
Why not just uncompute the W register?
Yeah.
Yeah. So you can try to. The problem is that if you try to uncompute it, what you'll see is that the overall thing is not projective. The projective version of this measurement will leave some garbage in the W register, and that you can't get rid of.
There's another question in the chat. Anurag?
Oh yeah, I can ask directly. So for me, is the procedure that you use to estimate the probability P in the approximate this Merritt-Waters construction, is it related to quantum phase estimation?
Yes, okay, absolutely, cool. Yes.
All right, got it. Great, thanks.
So maybe I'll just say a few words about this. So I guess that there's this algorithm that Unruh mentioned, quantum phase estimation. And morally, it does something very, very similar to Merritt-Waters. And the reason why they're sort of thought of as two different things was because at the time that Merritt-Waters' paper was written, the best guarantees on phase estimation were not so good, right? It would estimate your phase with some failure probability. And what Merritt-Waters showed is that you can make this failure probability like exponentially small. But since then, like phase estimation algorithms have actually improved, and it turns out by taking a whole bunch of like baby phase estimation algorithms, the same one that you have in Nielsen and Chuang, and taking a median of all the phases, you can drastically improve the error. And so using an improved phase estimation algorithm, you can actually subsume the Merritt-Waters technique. I think that maybe the reason to use Merritt-Waters is that it's so much simpler. Like you just alternate two things back and forth. You don't have to do like quantum Fourier transforms and stuff like that. You don't have to think about these median circuits. And the only price you pay for the simplicity is that it's quadratically slower. And in this setting, we don't really care about a quadratic slowdown in the reductions running time. So yeah, I mean, if the question's about general connections to other quantum algorithms, right, there's this other algorithmic thing that I'm doing here where I'm also using alternating projectors to amplify onto a state. And so what I'm doing here is actually sort of a Merritt-Waters version of a general quantum procedure called amplitude amplification. But the reason I'm using the Merritt-Waters version of it, again, is because of these issues with success probability. Right? So the way that you usually think about amplitude amplification is that you're trying to amplify into a subspace with some constant probability of failure. And if we did that here, like we would be, it wouldn't work, right? Because you can't incur a constant failure probability if you're a pair step every time. And so, Merritt-Waters is this way to ensure that if I'm in a subspace A and I want to go to a subspace B, then I can just keep alternating these two projectors onto A and B back and forth until B accepts. And I know that, as long as this accepts, my state is exactly where I want it to be. And this only fails with this exponentially small probability. So there's really there's basically two core subroutines here. A phase estimation to learn success probability, and an amplitude amplification to amplify back onto states with good success probability. But the key is that I don't want to incur any noticeable failure probability in either of these subroutines because I'm going to keep running them polynomially many times. And so that's why it's hard to plug in how these algorithms are written in the literature directly into our setting. And that's why we sort of do these like in-house solutions using Marriott-Watrous. And the nice property of Marriott-Watrous is your algorithms are really simple. Were there any other questions?
I think it's good.
Okay. Great. So let me just bring this home. Okay, so to recap the full rewinding procedure, how do I start with an initial adversary and get a bunch of transcripts? It's basically what I've been saying. There was one detail I was missing out, I wasn't mentioning, which was how do you get the invariant to be satisfied in the first place? Because so far we know how to say, if I have the invariant being satisfied, that Marriott-Watrous will likely output a high estimate, then I can satisfy it again. But it's not the case that the initial adversary satisfies as invariant. So the way that you satisfy it is fairly straightforward. You just run the Marriott-Watrous estimator. Okay, so you get some estimate P. If P is too small, you abort the whole thing. It's not worth it. But if P is large, then the invariant is satisfied. In particular, it's satisfied for P minus epsilon. This epsilon degradation is inherent. So after this initial Marriott-Watrous estimation, from this point on, you've kickstarted this procedure. You've satisfied the invariant for the first time, and now you can rely on this repair procedure to allow you to run a trial and then repair. But before I go on, I just want to recap here. When I'm running a trial and asking a question R and getting an answer Z, remember I'm doing it in this sort of careful, like lazy way, where I'm not actually measuring Z, but I'm actually first measuring if Z is accepting, and then only measuring Z if it is. So that's what this Z denotes. So anyways, I've disturbed my state. Then I run this repair step. And all this repair step does is takes my disturbed state S1 prime, introduces this W register of zeros, and then alternates my two measurements back and forth until finally the pi p minus epsilon star measurement accepts, discard my W register, and that is my repaired state. Now I satisfy another invariant, it's epsilon worse, and then I keep going. And that's it. That is the whole quantum rewinding picture for Killians protocol. And so for Kilian, right, you just instantiate this game to be the game at the end of Killians protocol. And eventually you're going to collect enough accepting transcripts that will either give you a PCP or a hash function collision. Okay, so just one quick concluding slide. The focus of this talk more broadly, right, was these problems that arise when you look at interactive protocols, which are some of like the most interesting results in crypto come up when you allow parties to talk back and forth. And in the quantum setting, security is really fragile because quantum adversaries don't play by your classical intuition. In particular, the key technique we use in thinking about interactive protocols and proving their soundness is this ability to say, well, if you could do something once, you can do it again. And this sort of allows us to really understand what interactive algorithms can do in the classical setting. But these techniques that we've relied on for so long just don't really apply to quantum attackers. And so today we focus on one key application of rewinding, which is to write down a lot of adversary responses. And the way we address this was by solving this abstract problem, which says that if a stateful quantum adversary is winning this challenge response game a single time, then given just one copy of its state, I can make this adversary win the game many, many times. So obvious next steps are, what are the other use cases for rewinding, right? This is, as I said, this is not the only kind of way we use rewinding in crypto. There's other things you want to do besides just record a lot of responses. So for instance, in applications such as zero knowledge, the goal may be to simulate the attacker's state potentially after recording a lot of responses. And so we give some answers to this in upcoming work with Alex Lombardi and Nick Spooner, and this should be out in hopefully a few weeks. Great. So thanks everyone for coming. Thanks for your attention. This has been a lot of fun.
Thank you. Fantastic. So let's see, are there any more questions?
Hey, Fermi, thanks for the awesome talk. So a quick question about the, you said that because you're not dealing with exact projectors, we have these approximate projectors. So when you do the alternating things a bunch of times, there's some degradation. Is this like a real problem, or like does it actually result in some loss in security as compared to like what Kilian achieves, or is this just totally like like it's not a real problem? I don't know if that question makes sense.
Yeah, no, good. So, I mean, one thing it does mean is that, because the success probability is going down, then you have to run for a little bit longer, right? So your reduction takes more time, right, to get the same number of transcripts that you do in the classical setting. So it does mean your reductions take longer, and so you get like less efficient adversaries that break your underlying hard problem. But the key thing is that you can tune the epsilon to be as small as you want it to be, any inverse polynomial. So in terms of like concretely, does it do worse? And like, I think the usual metrics, no. But like conceptually, yes, the reduction is running for potentially a little bit longer.
Got it. Thanks.
Sorry, just a clarification. And the more and the smaller you make your epsilon, the longer your procedure has to be, right?
Yeah. So I've been kind of vague about what I mean by this epsilon, but basically, if you have some success probability p, then it's almost always the case that it would be fine if it were p over 2. So you just set your epsilons so that you would never drop below p over 2, right? So you can do this if you know how many times you need the adversary to answer correctly.
Makes sense.
If I may ask about this, so about this reconstruction procedure, can you maybe go to the previous slide just so that I have it in front of me? This one, yeah. So this Marriott Watchers thing, it's like sort of, I'm not sure that I understand the invariant here, because you get the success probability and expectation. So can there be like some noticeable probability where you just fail and it throws you into a state where you cannot, from which you cannot recover, or something like this? Sort of it throws you into like a probability 0.
Yeah.
So what is the invariant here, and how does it sort of make sure that you can with overwhelming probability just keep going, you don't sort of fail in the middle?
Yeah, no. So okay, maybe I lied when I said this is the full procedure. We do these little checks here and there to sort of reset the error back down to this delta. And we do incur some failure probability. So for instance, once you have your repaired state, what you can do is just run a fresh Marriott Watchers estimator on this repaired state. And now this has sort of reset your failure probability back to delta. And you can, and then you can say, well, if this estimator gives you a really low estimate, then just abort the whole procedure. So yeah, in our full thing, there are these small, like negligible chances you incur that you fail and the whole thing's over.
So, I mean, in the initial estimator, if you fail, then you fail, right? Then you cannot proceed, right? I mean,
on the initial adversary, when I run, if MW estimator outputs something that's like negligibly small for P, then it's done.
But so why can this? So how come this cannot happen in your like sort of in the following MW estimator executions? Yeah, good.
So what we're basically maintaining is that right. So as I mentioned earlier, this Marriott Watchers estimator has a lot of variance in its outcomes. Right. The outcomes think of them as their outcomes between 0 and 1. And in that very first Marriott Watchers estimation, the only thing I know about this distribution of outcomes is that it can be arbitrarily well spread through 0 and 1, just that they're centered at P. Right. And it turns out that the thing that we're ensuring when we restore the state is that the outcome distribution of this Marriott Watchers estimator is really concentrated, like really, really concentrated around where it should be. Like that's the key thing that makes this work. Because if it weren't concentrated, then exactly what you're saying could happen. That if it's well spread, then I can measure it, get a really bad estimate, and it's over. But I have to make sure that every time I do the estimate, there's only a tiny, like negligible chance that it's far from where I want it to be. And so the key thing is that like the property of being in this pi p star subspace, as long as I alternate it with the right projector, is that once I get back to it, the thing we're proving is that the state we've gotten back to has a really concentrated like distribution of Marriott-Watrous estimates.
Okay, am I supposed to understand why this is the case, or it's like a technical, or it's a technical reason?
Yeah, so if you stare for a really long time, you'll see that the concentration you want is implied by this expectation I wrote down, but I don't think it's like super obvious.
Thanks.
Okay, good. No more questions, and let's move on to the panel. So
actually, Umesh, can I? Yeah, sorry, I have one more thing to that answer. So it just occurred to me to say this, that maybe think about like what this projector pi p star means, right? Like what it's saying is that like being in a projector, like if I have a projector in general and I have a state in that projector, what it means is that if I'm to measure that state with this projective measurement, then I'm certain about the outcome, right? Here, my projector corresponds to running the Marriott-Watrous procedure and getting an outcome that is at least p.
Right.
And what I'm restoring is I'm basically restoring the property of being in this image. And so when you translate that into what it's saying about Marriott-Watrous, it's saying that I have a state such that if I ran Marriott-Watrous on it, the estimate it spits out is at least p with overwhelming probability.
Why is it overwhelming probability? Because you landed in because you started from the subspace?
Yeah, so I guess what I'm saying is kind of approximate. Like this is not true for all states. And in particular, we only prove it for like the certain states we repair back to. But I'm saying intuitively, like think of being in a subspace as saying, well, my state has a property that if I did this measurement, I have certainty about its outcome. And I'm saying in this case, the measurement is I applied Marriott-Watrous and the output was at least p. And if I'm certain that this outcome will accept, or that this measurement will accept, that means that my state has a property that if I applied Marriott-Watrous to it, the sort of distribution is really supported on like p and greater. And so if that weren't the case, I wouldn't actually be in the image of this projector.
Okay, yeah, that gives an idea at least. Thanks.
okay, great. Okay, so thanks, Fermi. So let's move on to the panel. So Fermi, if you could stop sharing, and then I think we have the